So the last problem is a problem that deals with something we've looked at actually last semester, but we're revisiting because we have a new form of potential energy. Imagine we have the sun and the earth is orbiting at a distance, let's call r1. And then we're told that what happens if the earth stops revolving and then actually crashes into the sun. And now we want to find what is the speed as this happens. So if we use our conservation of energy equation that says mechanical energy of a system is conserved, that means that the kinetic energy plus the potential energy before has to equal the kinetic energy plus the potential energy after. And because the sun is so much larger than the earth, then we will have to assume very reasonably that the sun is not going to move. It's just the earth that's going to move due to the gravitational pull. And if we do that, then we can say that the kinetic energy before, which is 1/2 mv2 squared, plus the potential energy, and potential energy for gravitational is the g constant times the product of the masses over the distance. And when the crash happens, it's going to be the radius of the earth plus radius of the sun. Those are the distances from center to center. In K2, once it crashes, we know the earth is not going to be moving anymore, so we can say that's 0. And then the same for the potential energy. It would be G, mass of earth, mass of sun. But before, they had the distance between them, which we're calling R1. So R2, or in the case of the after, the distance between the sun and the earth is just from the center of the earth to the center of the sun, whereas before the collision, it's the actual distance from the earth's center to the sun's center. And if we solve for V2, we get that V2 equals square root of 2g mass of sun. Notice that every term has the mass of earth in it, so it can disappear. And if we factor that, then we have 1 over r sub e plus r sub s minus 1 over r1. And now, to find the velocity of the crash, we would fill in the values. So 2 times g, which is 6.67 times 10 to the minus 11 meter squared per kilogram squared. The mass of the sun is 1.99 times 10 to the 30th kilogram. Let's extend our radical. And then in here, we have 1 over, the radius of the earth is 6.37 times 10 to the 6th meter. And the radius of the sun is 6.96 times 10 to the 8th meter, minus 1 over the distance from the center of Earth to center of the sun in the orbit is 1.5 times 10 to the 11th meter. And if we do this, we get a value of about 6.13 times 10 to the 5th meters per second.